Okay, good morning. Have to hand it to you 20 to 30 who make it here by 8 o'clock in the morning. A lot of your colleagues apparently choose to sleep in. So good for you. Lab 2 is going on. You're working on assignment number 1. Just a reminder that the midterm exam is towards the end of October. I forget the exact date. It's 20-something, 29 or 26 or something like that. And just a reminder that it's in person here in this room that morning at 8 o'clock, okay? So just be prepared for that. I suspect it'll be a full house. The other 3/4 of your colleagues, I hope, show up. Okay, and other than that, it's business as usual. We are currently still talking about addressing modes. And again, I'll keep reminding you that right now we're talking about addressing modes that are commonly found in most processors. And when we're done this set of lecture slides, we're going to move on to the ARM processor. And for the next 2 or 3 days, we're going to look at the ARM processor's instruction set, its instructions in particular. And it uses most of these processing modes, or it has these addressing modes, available to you. Okay, and so the ARM is the particular processor that you will learn the assembly language of. Now, you're not going to learn it in its entirety. Once we get there, I'll show you a couple of documents that I put up on Canvas yesterday that you can refer to, and you'll see that there are lots of instructions, there are lots of options for each instruction. We're not going to get to that detail, so when you see that, don't panic or freak out. You're not expected to know everything in detail. It's just the basics that we're going to learn in this course with respect to the ARM processing language itself, okay? So for those of you who are really interested, you can dive into it and do a ton. It used to be that we had a project in this course. Last time I taught it, we did have a project in this course where you had to program something in the ARM assembly language. So you actually got to use it. We don't do that anymore because students complained they had so many projects. Every course had a project. So we got rid of it in this course, which is maybe not the best thing, but it was kind of interesting. One of your alumni, his name is Montana Reed. I don't know if you've heard of him, but he's a local guy, yeah, and he took this course with me, and his project was, he actually programmed a game. What's the closest equivalent to the game? It's kind of like Pac-Man, or was the snake game, where the snake gets longer the more things you eat up, and then eventually the snake hits itself, and that's when you die. He did something like that. It was amazing, right? Other people's project where, implement a simple calculator where you add 2 numbers together. And Montana, of course, had to program a video game. Anyways, that's what he did for a living, or he did for a very short time, and has been independently wealthy ever since. So there is money to be made in coding. He's a living example of it. Okay, so we'll look at the ARM processor in particular, but let's finish off with a few of the addressing modes that, again, most processors have in them. We are now looking at a couple of addressing modes, which we ended off last day, which are typical of CISC type of processors, complex instruction set computers, okay? Although the ARM is a good example of a RISC processor, which also has some CISC type of addressing modes and instructions. And these are some of them. So we looked at these last day, the auto increment and the auto decrement, which is a form of the indirect addressing mode. And remember, the indirect addressing mode is always identified, at least in these generic syntax that we've been looking at. The ARM actually uses square brackets, not parentheses, okay? But typically it's brackets or parentheses of some sort that indicate the indirect addressing mode. And the indirect addressing mode means the register inside can be treated like a pointer, or you can think of it like a pointer, which means it holds an address, a memory address. Okay, so the parentheses mean the effective operand, the effective address of the operand is in the register. The operand itself is not in the register. The memory address where it lives is in the register. Okay, so in this addressing mode, the processor is going to go to register RI. It's going to read what's in it and interpret it as a memory address, and then it's going to go to that address in memory, and it's going to get the operand from there. Okay, the only difference with the auto increment is that after the processor has read the address that's in register RI and goes and gets that operand, it then increments the address that's in RI, so that now RI is pointing to the next address in memory, okay? And this is very useful for when you're reading a number of numbers that are sequentially stored in memory, one address after the next, okay? So it means that instead of now the next instruction being add 4 to register RI so that it points to the next one, this addressing mode does it for you automatically, okay? And because the plus is after, it does that incrementing of the address in register RI after it's already used that address in RI, the original address in RI, to go get the operand. The auto decrement is obviously decrease or decrement the address in register RI, but because the negative sign comes before, it does it first. So first, the processor will decrement the address in register RI, then it'll take that new address, go to memory, and get the operand, okay? And the reason it does it in the auto increment, it does it after, and the auto decrement before, is because these addressing modes are typically used when we are accessing a stack. And a stack, I've talked about a little bit, we'll talk about a lot more in the course later on. A stack is just a region of memory where we store stuff, okay? And yeah, you know, once we get to stacks and talk about them in a little bit more detail, if you come back to this, it'll be obvious to you why we want to auto increment after and why we want to auto decrement before. Okay, so that's an example of that, and I think that's where we left off. And so here's a quick example. You know, here's some RISC style code. This is not code in any particular processor's instruction set. It's just sort of generic, right? That's all we've been looking at so far. So in this case, this is similar to what we've done before. We're adding up a bunch of numbers that are stored in memory, okay, where the first number is stored at the address num1. And the number of numbers that we're adding up is stored at the address capital N, okay? And that, if you haven't figured that out or noticed that, the convention in the textbook and in all of these slides is when we have all capitals like this, that's referring to a memory address, a label for a memory address. Loop itself is also a label to a memory address. It's the memory address where this instruction is stored, okay? And sum as well is a memory address. So in this case, we've got a move instruction. It's going to move the number that is stored at address capital N into R2, okay? Now this is, I misspoke. This is not actually a RISC style program. This is more of a CISC style program. In CISC type of computers, we often use the move to get a number from memory and put it into a CPU register. In RISC style processors, like the ARM, we use load and store to get numbers from memory and put numbers back into memory, okay? So that's a clue that this is more of a CISC style program, because it's using a move to get a number from memory and putting it into a CPU register, R2. Okay, so we've got the number of numbers, whatever that is stored at memory address capital N. We've moved that into the register R2. Cleared is just going to clear register R3. If it had something in it, it's all zeros now. Then we're going to move, and this is the immediate addressing mode because of the number sign, we're going to move the actual address num1. Okay, num1 is an address, so the actual address num1 is going to be moved into R4. So R4 is going to act like a pointer. It holds an address, a memory address, okay? Now we're going to add, and here we're going to use the auto increment mode. We're going to add the number that is stored at the address which is in R4, okay? R4 has this address in it. So the number that is stored at memory address num1 is going to be added to what's in R3, and the result is put in R3. Okay? And then the address that is stored in R4 is going to be incremented. So R4 now no longer holds the address num1, it's going to hold the address num1 plus 4 if we're dealing with a 32-bit processor, right? 32 bits, 32 divided by 4, or 32 divided by 8 gives us 4. Byte addressable memory, every byte in memory has a unique address, so if memory words are 4 bytes long, then the address of the first word is num1, the address of the next word is num1 plus 4, 4 bytes later, okay? So now R4 is going to point to num1 plus 1. We're going to subtract the immediate operand 1 from what's in register R2. R2 is our counter, it holds the number of numbers. So now R2 is going to hold small n minus 1, okay? And then we're going to branch if that result of the previous instruction is greater than 0. So if we haven't reached the end of the list, we're going to branch back to loop, and we're going to just keep doing this until we've added all the numbers up into R3, and finally R2 will, at some point, R2 will have 1 in it. We're going to subtract 1. The result is 0, which is not greater than 0. So this branch won't happen, and then we're going to fall through. We're out of the loop, we fall through, and we're going to do this move instruction where we're going to move what's in R3, which is the sum of the numbers, into the memory address sum. Okay? Any questions about this? Okay, so hopefully these are starting to make a little bit more sense to you. And again, this, we've looked at it's all generic code, so, sometimes, you'll see an add like this with only 2 operands. Sometimes you've seen add in the past with 3 operands, okay? And that all depends on the type of processor, right? We had those few slides where we talked about, instructions with two memory addresses, instructions with 2 registers, instructions with 3 registers. It all depends on the processor. When we get to the ARM, we'll see a specific example of an instruction set, and this will look a little bit different for the ARM. But the general concepts are all the same for all of these processors. Okay, example. This is not how we would actually write assembly language for a particular processor. These are just English words that we use to represent these instructions, okay? For a particular processor, there's what we call a mnemonic, and it's just an acronym. It's just a shortened form of these English words. So in a lot of processors, move would be MOV. The mnemonic for the instruction move would be MOV. Add is typically add. Subtract would be SUB, for instance, would be the mnemonic in some processors for the instruction subtract. Okay, so that's all. Itself is stored in memory. Okay, so your memory holds the actual instructions of your program. It also holds the data that your program is working with. Okay, so somewhere in memory there is a memory word that contains this instruction. Okay, part of that 32 bits of that word is reserved to specify which instruction is being designated. Okay, we call that the opcode for the instruction. Yep.
In the loop, the R4 with the brackets, that makes it a pointer, right?
It means it's interpreted as a pointer.
So why would you want to add just 1 to an address and then have a sum of addresses? Because that means that the R3, you're putting an address in really, and then you're summing all these addresses.
No, we're not summing addresses, we're summing the numbers at those addresses.
So,
because this is the indirect form, or the indirect mode.
So the indirect mode means it's storing an address, but you're taking the number from it.
Right, it means, the indirect mode means when the processor executes this instruction, it looks at what's in R4 and interprets it as an address. It then goes to that address in memory and gets the number that's stored there and adds that to what's in R3. Okay? Okay. Any other questions around this? Every one of these instructions here will have a different opcode, and an opcode is just, I forget what it is in the ARM. I think it's 8 bits are required for the opcode. Okay, it's just a unique patterns of ones and zeros that identify which instruction we're dealing with. Okay, so that's the assembler is the piece of software that takes this instruction and it determines what the opcode is for this, and it determines what bits need to be set to ones and zeros to indicate these, and it puts those 32 bits, it writes those 32 bits, which can then be stored in memory. Okay, and we call those ones and zeros. That's machine language. That is the object. So a few definitions moving forward, and we've come across some of these already. The first one is mnemonic. So if we go back to the mean by mnemonic, and when we get to the ARM, we'll see the specific mnemonics that are used. Okay, so when you actually write assembly language, you're going to write this for a particular processor, not this. Okay. Assembly language, obviously, is what we've been looking at with mnemonics, not with these English words that we've been using so far. We've talked about the opcode a couple of times. We'll come across that more and more, and when you read the textbook, you'll see that all the time. And the opcode, remember, each of these instructions. Okay, so the opcode, every code. The assembler is a program. It's written in some language, and it's a program that takes your assembly language code, which we call the source program, okay, and it converts it to machine code, or the object program, which is just ones and zeros. Okay, so it'll take each of the program. Okay, so just some definitions of some of the things we've talked about, but going forward we'll talk more. Okay, so let's talk about what we call assembler directives now. These are additional statements that you put into your code, and it helps the assembler figure out what to do with your code. Okay? These directives themselves don't actually show up, pardon me, these directives themselves don't actually show up in the object program, okay? They're just used by the assembler to help it figure out what the object program should look like. So in this example that we looked at previously, where it's the same, it's a program that does the same thing as what we just looked at, but it doesn't use the auto increment addressing mode, right? It just loads, it goes to memory, the memory address stored in R4, gets the number that's there, puts it into R5, adds it to register R3, and you can see this is a 3 register type of instruction. And then here it increments the memory address stored in R4, decrements the counter, branches if the counter isn't 0 yet back to here. So it's adding up numbers again, but with more of a RISC style instruction set. But in this type of program, right, we were using these labels for memory addresses in our instructions, loop and sum and capital N, num1, those are labels. Well, we have to tell the assembler, what do those labels mean, okay? We have to associate them with memory addresses. We also have to tell the assembler where to put our program in memory. We have that option available to us, okay? So here are, again, some directives that are commonly used. And in the next slide, we'll look at the particular directives that are used in the ARM processor, but they're all kind of similar, okay? So here's the same code. So when we write this code in our, source program, on your computer in an editor, you would write your assembly language program. It would look something like this. Here's all the instructions that we have here. The ... just means, there's more to this program than just adding up this list of numbers. So here's the instructions, and you'll notice that here we're using mnemonics for the instructions, okay? So in this particular instruction set, whatever it is, load, the mnemonic for it is LD, right? CLR for clear, MOV for move, add, subtract, branch if greater than. Okay, these are common mnemonics used in a lot of processors. We'll see a lot of these in the ARM processor as well. Okay, so here's our program. So for instance, in this particular generic processor, there's an assembler directive that tells the assembler where to store our program in memory, okay? It uses this keyword called origin, followed by 100, tells the assembler when you create the machine language for this program, you're gonna store it at memory address, starting at memory address 100. So at memory address 100, we have our program, okay, the individual instructions of our program. We can do the same thing for data, okay? So this origin down here says, okay, all the stuff that follows, let's start it at address 200. So the first thing we have is our label sum, pardon me. The first thing we have is our label sum. So since origin says start the data at 200, the next thing starts at 200. So sum is associated with memory address 200, okay? So when we use sum in our program up here, it's really address 200 that's going to be used, okay? We also have the keyword reserve, which means reserve 4 bytes for this thing called sum, okay? So that means use a full memory word for sum, assuming we got 32 bits per memory word, okay? The next one is n, another label that we use in our program, okay? And in this particular example, the keyword data word is used to say, put the number 150 at the address n, where n is going to be, 4 bytes after sum, because sum was reserved for 4 bytes. So at address 204, that's going to be associated with this label n, and you right away store 150 there. It's like when you declare a variable and initialize it at the same time, okay? So you can almost think of these as variable declarations, if you want, and for some of them, we're actually initializing these variables. We're storing numbers at these addresses, okay? The next one, num1, is going to start again 4 bytes after n, so num1 starts at 208, okay? And in this case, we're going to reserve 600 bytes. So that means num1 is at 208, and that was going to give us room for 600 divided by 4 is what? 200? No. 150, right? 150. So we're going to have 150 memory words reserved, and the address of the first one will be called num1. Now this says num2 all the way up to num_n. These labels actually don't exist in here, so I wouldn't have even written them there, okay? Because notice in our program that we only use the label num1. We put that address into R4, and then later on, we every time through the loop, we're going to increment that address. So the first time, R4 is going to have 208 in it. After the first loop, R4 will have 212 in it, 216, 220, etc., all the way up to 804, once we've gone to 150 numbers. Yes, sir?
So we said the branch was DR, or the new moniker branch was DR, and in the right-hand diagram, it seems like it's BGT.
Yeah, did we say BR somewhere else?
I think so.
Yeah. And again, these are just all examples. When we get to the ARM, we'll see exactly what they are for the ARM. Okay, but BGT is very common for branch greater than. Yeah.
What was data word again?
Data word just means the actual, it's like initializing the variable. So give it the value 150. Whereas reserve just means reserve this many bytes for this label. Okay, so the reserve is like declaring a variable. Data word is like declaring it and initializing it. Okay. And again, these are just examples to get you thinking about, well, what do, the actual directive names, again, vary from processor to processor. The ARM use slightly different ones, but the concepts are always the same, right? Telling the assembler where to put this stuff in memory, and actually you can give it you can initialize some of these memory addresses with actual values. Okay, so that's all I want you to see here. So we'll look at the ARM in particular. Right? The ARM uses slightly different words for the directives, but they all kind of mean similar things. For instance, the ARM assembler uses, you can use the keyword area in your ARM code to indicate the beginning of a block of memory that corresponds to data or instructions. Okay, we'll see how this is used in a minute. Entry just tells the assembler, okay, what comes after this word entry in my source program is the first instruction of my program. Okay, it's kind of like the start of the program. And end is the end. The last thing that should be in your ARM source program should be the directive end. If you want to initialize a memory address with some value, you can use EQU, which means, equals or equate. Okay, so it's used to declare symbolic names for constants. Oh, I'm sorry, other way around, yeah. So this is where you want to associate a particular address with a name with a memory address, where DCD actually labels and initializes a 32-bit value, DCB an 8-bit value, DCW a 16-bit value, or DCS a string of 255 bytes. So, and we'll see how we use these in an example. So this is how you actually give a memory address a value, whereas here you're saying, well, this label means this. Okay, so let's 32-bit value. Okay, let's look at an example here. So here we have some ARM code. Okay, so you can see that the ARM mnemonic for load is not LD, it's LDR. Okay, so this is your first example of an ARM assembly language program. So we've got some statements here, and we're going to look at these in details in the coming slides in the next 2 or 3 lectures, okay? So don't worry about exactly what these mean just yet, but just notice, we have labels called pointer, we've got a label called loop again, because we've got a loop going on here. We've got a memory address, which uses the label sum. It's the same kind of code that we've been looking at before. Okay, so the assembler directives, though, are what we want to pay attention to. So, we have this as a directive called area, which tells the assembler, okay, this next block until the next area is my code. Okay, and it's just a way to sort of organize your code. Whereas down here, this block of stuff is what we're going to call data. Okay, entry just says, okay, the next thing to come is the start of my program. So the next thing to come is here. End says this is the end of my program. Okay, that's all there is to it. Nothing really crazy here. Okay, the assembler has to know where it starts, it has to know where it ends. Okay, and then we've got the same kind of thing as we saw in the previous case, but we use different keywords in the ARM for these directives. We're using DCD, so DCD is going to say, okay, well, sum, this label sum, is going to be initialized. DCD is so it's going to say reserve 32 bits in memory, associate the address of that 32 bits with the label sum, and put a 0 there. Okay, that's what DCD does. So it's like declaring and initializing a variable. Now notice here in ARM, we're not actually telling the assembler what memory address to put it at. Okay, so presumably the assembler will choose where to put this stuff in memory. All you're saying with DCD is reserve a memory location somewhere, associate the address of that memory location with the label sum, so that when I use sum here, I'm referring to that particular address in memory, and store the number 0 there. Yes, sir?
What if we did want to declare a specific location?
There's probably a way to do it. I forget now how. I'd have to go back and look at the instruction set reference. Sorry, I don't remember offhand. Okay, and all of these are the same. Notice that, though, in the case of the last one here, remember num1 in this example program was the address of the first number in our list of numbers that we're going to add up. Okay, so you'll notice here that we can have a number of numbers separated by commas. 3 will be stored at the memory address associated with num1. Negative 17 will be stored at the memory address of num1 plus 4. Okay, 27 at num1 plus 8, etc. So we can initialize a bunch. It's like initializing an array in your C++ program, right? We can store a number of different numbers at sequential addresses in memory.
But they won't be labeled they won't be labeled num2 through
No,
whatever.
no, there's only one label called num1, and it's the address of the next one, right? So in our program here, we load in, here, num1 is associated here. So you can see here, we have another address or memory location. Its address will be associated with the label pointer, and what we store there is an actual address. It's the address num1, which is the address of 3 in memory. So we're going to use pointer as a pointer. That's why we call it pointer. So somewhere in our program here we have pointer. Well, what is pointer? It is an address in memory, okay? And what's stored at that address in memory? Another memory address. The address associated with num1. That address holds 3. Okay? And then I said that because, right, there is no num2, num3, num4. Those labels don't exist in our program. We put num1 into pointer, right? And then that gets put into R2, so R2 then gets incremented later on, and we're going to see how that works in a second. Don't worry about this just yet. Okay, so those are just examples of assembler directives. Okay? Yeah.
The assembler directives at the bottom, like the DCD, do we have to type that out, or is that?
Yep. This would be your whole source program. You would have to type this into your editor, and then you would hit assemble, right?
Well, shouldn't the loop itself figure out all the math, like the 3, -17, 27?
No, these are the actual numbers we're adding up.
Oh, okay.
Yeah. So we have to tell the assembler to store them somewhere in memory. Yeah.
So it seems like when you use your hashtag, you could instead be using, like an R1 or an R2, right? If you had
Like
these
here?
stored,
Like-
but does the hashtag save in memory?
You mean these, right?
Yeah, but when you're.
They mean the immediate addressing mode,
Right.
which means the actual number 0 here gets put into R0.
So that saves memory versus declaring an R6 for 0 and an R7 for 4.
Instead of clearing,
Declaring, sorry.
declaring.
Yeah. So we declare a space in memory for 0, for 4, and for 1.
You could do that and then use a label here if you wanted.
Yeah.
Yeah.
Does it save memory using the hashtags?
Yes, it would, because in this case, this value of 0 is actually stored in the 32 bits that house this instruction. Whereas if you use the label here, that label would need a separate memory location than this one.
Okay.
So that's true, yeah. Yes.
When the pointer is called, would it call the whole array that's in DCD or just the
No.
first?
Pointer here is a memory address,
Yeah.
right? That memory address holds another memory address.
Yeah, but num1 has an array in it, you said.
No, num1 is the address of the first number of your array,
Oh, okay.
right? So we've got in memory, we've got this. Here's num1. It corresponds to that memory location. It's got a 3 in it. The next one, -17. The next one, 27, -12, 322. Okay? There are no labels defined for these memory locations. Okay, and we'll look at some of these instructions here in a second. Okay, so that's all I wanted to say about assembler directives. All right, so let's talk a little bit now about, we're gonna jump around a little bit because, you know, it's kind of hard to do everything, talk about everything with instructions, and we want to start talking about some of the other things that are going on in a computer other than just the code itself. So you'll remember way back at the beginning when we looked at a high-level block diagram of a computer. Well, one of the functions that has to be implemented in a computer is talking to the outside world, right? We call that input and output. So we want to start looking at how we actually do that at a software/hardware level, okay? So input-output devices are things like keyboards, mice, monitor, anything you would connect to a computer, a printer, et cetera, okay? Now, input-output devices and CPUs operate at different speeds. What do you think is faster, your input-output device or your CPU? CPU, right? CPU is way faster, and really. So how do we handle this? Well, we need to synchronize things somehow. Okay, you've got one thing, it's like, you guys are way too young, but in the original Star Trek episode, there was any Trekkies here? Anybody watch the original Star Trek? 1, 2, 3, okay. Well, there was an episode where something comes onto the ship, the Starship Enterprise, and it's operating at light speed. I forget exactly what it was, some entity, right? It's operating at light speed, and Captain Kirk, the hero of the show, somehow gets transformed so that he also operates at light speed. So everybody else on the ship is like this, right? And he thinks they're all frozen dead or something. You guys remember this episode? Yeah, right? No? You didn't see that one. Okay, so they weren't frozen dead, they were just moving really slow, right? And he was moving normal speed, and what's wrong with you guys, right? And he finally figures out. Anyways, it's kind of like that, right? The CPU is like Captain Kirk operating at really fast. Everybody else is sort of frozen, moving really slowly. That's your peripherals. So we need to synchronize them somehow so that they can talk to each other and data can be transferred between the two of them, okay? So one very common approach is what we call polling. Since the CPU is the faster thing, it's basically always waiting for the input-output devices to hurry up and do something, right? It's waiting for you to press a key, or it's waiting for the display to be ready for the next line of data to send to it, okay? So polling means the processor is constantly asking the input-output device, are you ready? Are you ready? Right? It's asking the keyboard, do you got a new character for me? You got a new character for me? You got a new character for me? Right? And it's going to ask, 1,000,000 times before the keyboard actually has a character for it. Or it's going to be telling the display, are you ready for the next line of data? Are you ready for the next line of data? Okay, so polling means the CPU is asking the device if it's ready, either to give it the data or to receive data, okay? So our programs are actually, when we write our program, we write it in such a way that we're polling the device. So we write assembler language, which is asking the keyboard, do you have a new character for me? Okay, we write the instructions in our assembly language program to do that. We call this program controlled I/O. Okay, so it's the actual program that we write that is controlling this interface between the CPU and the I/O. Okay, it should be on the previous slide, right? Your keyboard, if you're a fast typist, the best you can do is a few characters per second, right? So we're talking, I don't know, if you can type 4 characters a second. I know I can't, but if you could write, every character requires 8 bits, the ASCII code. So 4 times 32 bits per second, okay? That's about as fast as somebody could write or generate 32 bits of information per second. Well, obviously your CPU is way faster than that, right? It can run at millions of instructions per second. So the CPU is infinitely faster than what you can generate, the data you can generate on your keyboard. And the same is true of a display, right? A display can only handle a few thousand characters per second. Printers, maybe a little bit more. Okay, so the difference is, or the important thing is there's a difference at the speed at which the CPU, the computer runs, and at which the peripherals, the things that are connected to its input and output ports can run. So we'll talk about how we do that in a second. Physically what's going on is obviously we have our processor here. We're going to be focusing on the keyboard and display. So here's our keyboard. Okay, so this big box here represents the actual physical keyboard. This is my computer here, or my processor. Here's my keyboard, and here's my display. Okay, in order to do this back and forth of data, Obviously, they all have to be connected with what we call an interconnection network, right? It's the cables that connect my keyboard to my computer, that connect my computer to my monitor. That's the interconnection network. So in order to do that, we're going to have some special circuitry in the keyboard. We call it an interface circuitry, as well as some special circuitry on our display called the interface, okay? Our processor, of course, consists of, our general purpose registers, our CPU, the control registers, all the stuff that we've been talking about and will continue to talk about through the course. But the important thing here is in the interface circuitry, in the keyboard itself, we have some actual registers. Okay, so there's a small amount of memory in that keyboard, and we have registers, and the two we're going to talk about right now are the data and status registers. So this data register is the place where when you press a key on your keyboard, the circuitry in the keyboard goes, she pressed the W, I have to put the ASCII code for W into my data register. Now that W can be transferred over the cable to the CPU, okay? Other way around in the display, I've got a data register as well. So when the display is ready for the next line of data to display, the CPU is going to send that data over the cable and write it into this register called the data register in the display. And then the display is going to display it. Now there's a couple of other registers. We're going to use the status and control register that control this whole process, and we'll talk about that in a second. But that's the general thing that's going on here, okay? So, the instructions in your program that are running on the processor are going to be polling the keyboard, for instance. And so it's going to send a message to the keyboard saying, well, it's not going to send a message, it's actually going to read the processor is going to read what's in the status register. A certain bit will be set if the keyboard actually has a new character. And when the processor says, that bit's set, okay, well, I'm going to read my the new character out of the data register and bring it back into the CPU, okay? So on the keyboard is in a keyboard, it just knows it's a memory location out there somewhere that it can access, okay? We call that memory map register, yeah. To do that, these registers in the interface circuitry on the keyboard and in the display, they have to be accessible by the CPU in the processor, okay? Just like the CPU can access its own registers, okay? We call this memory mapped I/O. So the CPU can access these registers in the keyboard, in the display, just like it can access its own registers or memory addresses in the main memory unit, okay? So as far as the CPU is concerned, it doesn't even know this register I/O. So when the I/O buffer registers, like this data register, are referenced by the program as though they were part of the memory space. So that means all the instructions that we can use on memory addresses, we can also use for these registers on the keyboard and on the display, right? We can move numbers in or out of them, or depending on the instruction set architecture, we can use load and store to get those numbers or write them back in. And we're going to use status bits located in the status register in order to control this whole operation. Okay, so how do we do it? Status. Okay, well, let's look at, here's that same figure that we saw before. Let's focus on the keyboard for a second. So the keyboard has these three registers in its interface circuitry. Here are the three registers. So the keyboard data register only needs to be 8 bits long, because when you type a character, you only need the ASCII code to represent that character, and the ASCII code is only 8 bits. Well, 7 bits actually. It fits in a byte. So that register here, right here, this data register is just 8 bits long. Let's call it keyboard data. We also have another register that's 8 bits long. Call it the status register. And one particular bit in that status register is going to be used to tell the processor whether there's a new character stored in my data or there isn't, okay? If there's a 1, for instance, that means there's a new character stored in the data register. If there's a 0, that means there is no new character. It's still the old character that you read a long time ago. Don't worry about these other 2 bits. We're going to talk about those next lecture or 2. Okay? So as far as the processor is concerned, all it has to do is it has to, or before I get there, and each of these registers in the keyboard interface circuitry, which are on board with the keyboard, can be accessed by the CPU simply by referencing some memory address. Okay? So the keyboard registers are assigned an address in the memory space of the computer. Okay? They're not part of the memory unit itself. Physically, they're actually memory locations. They're registers on board the keyboard. But they're given unique addresses that are part of the address space of the computer. So in this example, 4000 is the address for your keyboard data, 4004 for the status, 4008 for the control register. Okay? So that means the CPU, when it wants to figure out, is there a new character waiting for me in the keyboard, all it has to do is look at this memory address and look at this second bit of the word that's stored there, or the byte that's stored there. If it's a 1, it says, oh, there's a new character waiting for me in the keyboard. It can then access this memory location, 4000, and read in this into some one register in the CPU, for instance. Okay? So that's all there is to it. Likewise with the display, it's just the other direction. But the display itself will have 3 registers, memory locations that are actually physically located in the display, but they will have unique addresses that are part of the address space of the computer. So the computer can reference the data display, the display data status register in the display by referencing address 4010. So you can use all of your load and store instructions in your program to go and read in what's there. And same thing, there's going to be a particular bit, maybe bit 2 of the status register that is going to indicate whether the display is ready to receive more data or not. Because remember, the CPU is running way faster. When your program runs, you can pile data into that display at light speed. The display can't handle it that fast, right? So you have to have a way, the computer has to have a way of determining when is the monitor ready for the next data, okay? We can use a bit in the status register to indicate that. So when the display has processed the data that was stored in this data register by the CPU, right? 1 row of pixels, for instance, it says, okay, I'm done with that data. It's going to set D out to 1. And now the next time the CPU pulls this status register, right? The next time your program reads in what's here, it's going to, you can test to see if this bit is a 1. If it is, you now know, or the CPU or the program knows, the display is ready. So now I can write new data into here to this memory address. And then the process continues. Okay, so that's what we call memory mapped I/O. Memory mapped means these registers in the input-output devices have addresses that the CPU knows and can recognize. And polling means the CPU is constantly reading this status register in the display. It's constantly reading this, maybe in a loop, right? It's going through this loop and it's reading. Is D out of 1? Nope, okay. Is D out of 1? Nope, okay. It's going to keep doing that until finally the display sets D out to 1. Then the next time your program pulls this status register and looks if this is 1. Oh, it's 1? Great. Now I can send out data to the display. And then it does the same thing. And then it keeps polling and waiting for the display to process that data. Okay, so that's what we call memory mapped I/O. And so here's a simple program that we will finish on Wednesday. Okay, so this is not ARM code. This is just generic type of code. Okay, and you can see we've got a couple of loops here. We've got a loop where we're going to be constantly reading the status register. And we're going to be checking if a particular bit is equal to 1. When it is, we're going to branch. We're not going to branch. We're going to read in that data word that the keyboard has, and then we're gonna actually display it. Okay, so we'll look at this in detail on Friday. Today's Wednesday. Okay, we'll see you then.